Sastri udah masuk. Polisi ya. Kerancang baru.
Assalamualaikum Ibu Gaby.
Nah, ini persis selesai 40 masuk lagi ke sini.
Oh, iya.
Dengan Pak Asep.
Hai, Prof Naresh.
Hi, Vidya.
Oh
Good,
iya,
good,
udah
good.
ada.
Good, thanks.
Yeah. We have Prof Asep. Assalamualaikum Prof Asep. Sorry, you are still muted, Prof.
Okay. Good afternoon, Professor Naresh.
Hi, good afternoon.
Good afternoon. Nice to meet you again.
Yeah, that's right.
Yeah.
I was going to say Selamat Sore.
Oh,
Yeah.
Selamat sore.
That's good.
Sundanis. We are in Bandung. West Java. So our tribe is Sundanis.
All right.
Can call Wilujeng Sonten.
It's a bit harder.
That's a little difficult. I'm learning slowly.
Wilujeng Sonten.
Okay.
Looks like there is a news of new virus now. It's
Yeah.
Australia stopped the people coming in for 2 weeks.
Oh yeah. Yeah.
So they put restrictions for 2 weeks.
Yeah. Indonesia still accept the tourism.
Okay.
Indonesia, but what I mean, they have to follow some regulation.
Yeah, that's true. That's true. Mm.
And for what I mean, for New Year's and Christmas, our government implement the lockdown again with the
right,
third level.
Okay. Yeah, it's a bit difficult to predict.
Yes.
Yeah.
So, do you have idea how to restrict the spread out of the virus?
I think it's just taking precautions and maintaining, I think, masks and hygiene. That's the main thing, I think. And also they're saying more population has to get vaccinated. Because if more people get vaccinated, then the virus have less chance to spread. The new strain Omicron, they are saying that is not very virulent. It spreads very quickly, but it's not virulent. So that means it's good for people's immunity. So, but it's hard to predict which way it's gonna go. I was listening to a virologist this morning, and he was saying that the virus, they change all the time. It's like the cold flu virus changes every year. Same thing with COVID virus. It'll keep on changing. We just have to be prepared.
Yeah. Can vaccine inhibit the virus spread out?
Vaccine, yes, it does. Yeah, because I think vaccine, the two things with vaccine. One is that the people don't have to go to hospital. If you have vaccine, then there's less chance to go to hospital. But vaccinated people can spread the virus. I think that's what the papers are saying. But maybe it requires, for the virus to spread, it requires a bigger dose. Like if the people are vaccinated, they give out less dose of the virus. If they're not vaccinated, then they can give lots of virus particles. So maybe that's why there is higher spread of virus when people are not vaccinated.
I mean, with the new strain.
With the new strain, apparently they're saying that if you get a booster shot, then I think you will be safer from that.
I see.
They're saying that the Pfizer, I think, vaccine works against that virus.
So you recommended to do the booster, yeah?
Yeah, I got already.
Yeah, I haven't. I just twice the vaccine, but hasn't booster yet.
I got mine 3 weeks ago, third one.
What is the impact of the booster to our body?
I actually felt for 2 days I was little little feverish and bit of pain for 2 days.
So you feel the impact of the vaccination process, yeah?
Yeah, it was more than the second dose. I didn't feel anything in the first dose, because first dose I went to work, so no problem. Second dose was only half a day and there was no problem. And third one, I found it was roughly 2 days it took for me to be 100%.
Yeah. Okay.
Yeah. Well, I was talking to one of my friend. She's a virologist, and she's saying that it's very important to get a booster. Yeah. Because she's saying that if you have Pfizer vaccine, Pfizer loses its capacity after 3-4 months, or it's reduced quite a lot.
I use lavender oil and cajuput oils.
Okay.
To prevent the Pfizer attacks.
Yeah, I mean, yeah, some people are in Australia are trying the tea tree oil. You know, there's a tea tree oil, which is a natural product. It has antibacterial properties as well. So they are trying that as well.
Yeah.
You can spray in the room. They can spray it in the room.
Yeah. So I use this is the what I mean diffuse.
Oh,
Yeah. At my room also.
That's good. I think we have to try everything we can.
Prof,
But I agree with you. Yeah, I agree with you to what I mean to do the booster. Maybe one alternative. Yeah, why? Because booster is more effective. Maybe.
Yeah. Okay.
Okay. Sorry, Bu Pidia. Yeah.
It's okay. Yeah, so it's gonna be an interesting discussion actually. But shall we start now? It's 2:47 here in Bandung, so let me record first. All right, good afternoon, everyone. Good evening, Prof. Naresh. Good afternoon, Prof. Asep, Ibu Gaby, Ibu Amelinda, and all students. We are now having the 7th lecture from Professor Naresh. And yesterday, Professor Naresh already explained about the reaction of carbonyl compounds, that carbonyl compounds can react with water and then alcohol, amine as the nucleophiles. And yesterday we also learned about the carboxylic acid, and maybe Professor Naresh will continue the lecture about the carboxylic acid. And after that, we will go to the alkene. And I think it's your time, Professor Naresh, please.
Thanks. I'll start sharing my screen.
Sure, yeah.
Yeah. Okay. I'll make it a bigger screen. Yep. All right. I just grab a pen. Okay, great. All right. So today we're gonna continue with the carboxylic acid topic, or carboxylic acid derivative topic we started in the last lecture. I'm going to try to make the lecture a little bit simpler today, because I felt that it was getting a little bit complicated for some students, and I'm going to give you a very simple introduction to carboxylic acids first, and then look at some of the reactions of carboxylic acids. As we learned in the last lecture, the carboxylic acid is a structure where the carbonyl has an oxygen functionality attached to it. And if it's an OH group, then it is a carboxylic acid. And if it's an oxygen and a carbon group, then it is an ester group. Then we learned about activated forms of carboxylic acids, which are acid anhydride and acid halide, and obviously the amides, which are very important molecules biologically as well. And we also learned that the difference between an aldehyde and a ketone carbonyl and a carboxyl carbonyl is that the group that is attached to the carbonyl group in case of carboxylic acids can be lost during the reaction or can be replaced by the nucleophile. So that means nucleophile can come in and kick out that red group which we have. While in the case of aldehydes and ketones, where we had a hydrogen or a carbon in its place, that was never lost in the reaction. They were always there in the product. So let's just have a brief introduction to carboxylic acids so that it is a little simpler for you to follow, and then we'll come back to the reactions of carboxylic acids and derivatives. Carboxylic acids are very common in nature and laboratory. If you look around, you will find many, many carboxylic acid compounds in the nature as well as in industry. And structurally, they resemble aldehydes and ketones. As we learned, they have the carbonyl group. And the carbonyl carbon is sp2 hybridized. We know that the carbonyl group is planar. And the carboxylic acid group altogether is planar as well. And we'll see that there is a resonance structure you can write if you remove that proton, which makes the carboxylic acid planar. And we'll look at that shortly. Another thing about carboxylic acids is that the carboxylic acids can form hydrogen bonds very easily. And hydrogen bond is typically between an oxygen and a hydrogen, or a nitrogen and a hydrogen. And the carboxylic acids can form hydrogen bond with water, as well as they can form hydrogen bonding with themselves as well. And a net result of this hydrogen bonding that is present in the carboxylic acids is that it raises their melting point and the boiling point. So if you look at the boiling points of carboxylic acids and their melting points, they are much higher compared to other organic compounds which might have similar molecular weights. And that is because of the hydrogen bonding that is present. And hydrogen bonding also improves their water solubility as well. So many carboxylic acids, they are soluble in water, particularly acids which are less than 6 carbons. If the carbon chain length is more than 6 carbon, this is greater than 6 carbon, then their solubility decreases in water. Say, for example, if I just have acetic acid, which is just 2 carbon compounds, CH3COOH, it will be totally soluble in water. This is vinegar. But if I take an acid which has, say, 7 or 8 carbon chain, if I say it has CH2 more than, say, 6 or 7, if I put 6 of them here, that becomes like an 8 carbon acid. That will have very low solubility in water. So the shorter chain carboxylic acids are soluble in water, and the longer chains are not, because they have a long alkyl chain. And carboxylic acid by nature are acidic in nature. That's why we call them acidic, because they are acids. And definition of an acid is that the acid is able to give away a proton quite easily. And in this case, it happens. And also, carboxylic acids are able to react with bases, because we know an acid reacts with a base to form a salt, right? So carboxylic acid react with bases to give a salt. That proves that the carboxylic acids are acids. And the interesting thing is that the salts, once you react a carboxylic acid with the base, you will get a sodium salt. And the sodium salt has much more solubility in water compared to the carboxylic acid. Say, for example, if you take this acid here, this acid is called as benzoic acid. That's an aromatic acid, benzene ring with a carboxylic acid attached to it. It's called benzoic acid. Benzoic acid has poor solubility in cold water. If you want to dissolve benzoic acid in water, you have to heat it up. Only then it dissolves. But if you take the sodium salt of benzoic acid, it is very soluble in water. You can dissolve it even cold water. And you will be surprised to know that benzoic acid is a preservative. It is added into a lot of fruit juices. It is added into a lot of foods like bread because it can kill bacteria. It can keep the food fresh. It can keep the food from spoiling. So benzoic acid is antibacterial and it is added quite a lot in food. Sometimes there's a number written, the bottle might say that it contains a preservative 220. 220 typically means benzoic acid. But benzoic acid also have low solubility in water. So if you add benzoic acid into orange juice, it's probably gonna start to precipitate out when the juice is gonna be sitting in a fridge. But if you add sodium benzoate, which is a salt, this would not precipitate from the solution. It will stay in the solution because it has good solubility. So many times you find that orange juice might have two preservatives rather than one. And one preservative might be the benzoic acid, and the second one might be the sodium salt of benzoic acid, because that has much better solubility in cold solution or cold water. The same thing happens with aspirin. I don't know if you have used aspirin before. You can get aspirin which is soluble in water. You take the aspirin tablet, you put it into water, glass of water, and you see a lot of bubbles coming out, and the aspirin dissolves in water. And if you take aspirin which is not soluble in water, it will just stay as a precipitate in water. So what's happening in the soluble aspirin is that we are forming a salt of aspirin, and salt of aspirin is soluble in water, while the aspirin itself is not soluble in water. So the salt can be used to improve the solubility of many different types of molecules, particularly drugs. How acidic are the carboxylic acid? Can we tell, can we measure, or can we get an idea of the acidity of the carboxylic acid, that how acidic they are? Here, I got a table which has HCl, acetic acid, water, ethanol, and alkyl halide. What I want you to look at is this pK value here. We don't want to worry about the melting points. We want to worry about the pK value. But if you want to look at the melting points and the boiling points as well, you can see that the carboxylic acid here has a much higher boiling point than the ethanol molecule. It's the same carbon chain, 2 carbon, 2 carbon, 2 carbon. This has much higher melting point as well as boiling point. But what we are interested in is acidity. Acidity is normally measured by this value here called pKa. If the pKa value is lower, that means the compound is more acidic. Like, for example, HCl, which is like a strong acid. It has a pKa of -7, while acetic acid has a pKa value of 4.75. And if you look at water and ethanol, water has a pKa value of 15.74, and ethanol has a pKa value of 16. So lower this number, more acidic the compound is. So that means acetic acid is more acidic than water and ethanol. So this number here tells us that acetic acid is acidic, but it is much less acidic than strong acids like HCl, H2SO4, and so on, but it is still acidic in nature. So what's the reason why carboxylic acids are acidic? Carboxylic acids are acidic because they are able to give away this proton which is attached to the oxygen. And if you give away that proton, you're going to get the corresponding anion and the proton H+, which going to become part of the reaction with the base. So what we are doing is we are comparing an acetic acid with ethanol molecule to see why acetic acid is acidic while ethanol is much less acidic. If you treat acetic acid with sodium hydroxide, this proton is given away, go to the OH minus, becomes water, while the acid becomes CH3 C double bond O minus, and you get the sodium salt formed with that carboxylate. We call that a carboxylate. An identical reaction with ethanol and sodium hydroxide, you can write it as an alkoxide. So that means oxygen by itself. There's a carbon, there's no carbonyl in it, and plus water. Same reaction written for both cases. But this carboxylate ion is much more stable than the corresponding alkoxide ion. The reason for that is that this can have a resonance structure where the negative charge can be delocalized. So in the case of alkoxide, the second structure, the charge is localized on one atom, that the charge resides on the oxygen only. So just take you back, we are looking at the bottom reaction here. The charge is on the oxygen. It's not delocalized, it's just present on oxygen all the time. It is not present anywhere else, it's not delocalized. But if you look at the carboxylate ion, CH3, C double bond O minus, you can write a resonance structure where the negative charge is delocalized. So if the charge is delocalized, then that lowers the overall energy of the anion. So that means this anion is of lower energy. That means it will form happily and be stable, be resonance stabilized. Hence, the carboxylic acid is acidic compared to ethanol, for example, because in ethanol, the negative charge on the oxygen is localized. It can't have a resonance structure. It just stays there. While in the case of carboxylate ion, the negative charge can be delocalized from one oxygen to the other. And this leads to lowering of overall energy of the anion, and hence it's easy to remove that proton from the carboxylic acid. We learned in the last lecture that the carboxylic acids, they are very sluggish to react. If I take a carboxylic acid here and try to react that with, say, an alcohol, say R-OH, which is representing an alcohol, or I try to react it with an amine, you will find that the reaction will be very sluggish. It wouldn't happen very readily. So what can we do to make this carboxylic acid react very quickly with alcohols and amines? We will come to the reactions of alcohols and amines with the carboxylic acids in a minute. But these reactions are very sluggish. They can happen. I'm not saying that the carboxylic acid cannot react with alcohol or amine. What I'm saying is the carboxylic acid reacts very sluggishly, very slowly with the alcohols and amines. But this reaction can be made to go much faster if you can convert this carboxylic acid into an activated form of carboxylic acid, which we call acid halide. Okay, and this is called acyl halide or acid halide. And these compounds are much more reactive than the corresponding carboxylic acids. And these can be made quite easily in the lab by using this reagent called thionyl chloride or phosphorus trichloride or phosphorus tribromide. So these reagents can be used to prepare the activated forms of carboxylic acids. And we will find that these are going to be much more reactive. And also we're going to learn why an acid chloride is much more reactive than carboxylic acid. At the moment, I'm just telling you that this is more reactive than that. But you might ask me, what is the proof? What is the reason why this is more reactive than that one? And we'll come to that reason shortly. So these can be made by reacting the carboxylic acid to the corresponding Cl compound. And this reaction involves an intermediate step where the oxygen of the carboxylic acid is replaced by the thionyl group which we had, or the phosphorus chloride group we have in the reagent. So initially this is formed first, and I explained to you yesterday how this is formed. And then the chloride minus comes and attack that carbonyl, kicking out SO2 and Cl minus in the process to give us this RCOCl. So you don't need to worry too much about the intermediates which are formed in this reaction. What you need to know is that the acid can be converted into the acid chloride, which is much more reactive, and chloride minus is a very good leaving group. And we'll learn in a minute why Cl minus, chloride minus, is a very good leaving group. So don't worry about the intermediates, but remember that acid is converted to the acid chloride because it is much more reactive. And the other form of carboxylic acid, which is also very active, is what we call an acid anhydride. And we saw the example of acetic anhydride yesterday, which is a very commonly used reagent in the laboratory, which is also an activated form of carboxylic acid. And we learned in the last lecture that acid anhydrides can be formed by removing water from the two carboxylic acid molecules. So if I just write down two carboxylic acid molecules side by side and remove a water molecule from it, you will find that we will get the corresponding acid anhydride. So if I put C double bond over here and another R here, and then I say I'm going to remove a water molecule from the middle, you will get RCO, oxygen COR, and that is your acid anhydride. The other way to get acid anhydride is to react the acid chloride with the carboxylate to give you the acid anhydride. So these are what we call activated forms of carboxylic acid. I left you with two slides yesterday asking you to think about those two slides. And if you can understand these two slides, then you can understand the reactivity of the carboxylic acids and their derivatives. There is a one difference between the reactivity of the aldehydes and ketones and the carboxylic acid. And that is the presence of this functionality. We are calling that Y. And the Y is just like the oxygen functionality we have in the other slide, can be OR, can be Cl, can be amine, can be anything. If you compare that with the aldehydes and ketones, I'm just reminding you again that in the aldehydes and ketones, the group that is present on the carbonyl, say if it was ketone, these two groups are never lost in the reaction of aldehydes and ketones. They always stay in the product. But here in the carboxylic acid derivatives, this Y group can be lost or can be replaced by the nucleophile. So Z minus is our nucleophile, but this nucleophile can be just lone pair of electrons like we saw in the case of aldehydes and ketones. So if this nucleophile attacks that carbonyl, you're going to get this intermediate like we also got in the case of aldehydes and ketones. But the difference here is that if this pair of electron comes around, you can kick out this Y group as a Y minus group. So this reaction is going to give you that plus Y minus. So the question then arises is what determines that the Y minus is lost in that reaction? Why can't we say that oxygen minus can come around and kick out the Z out? Instead of kicking the Y out, why can't we kick the starting reagent out? So there are three scenarios possible. One is if Z minus here is a very strong base or a very strong nucleophile, then Y minus will be eliminated because Y minus is weaker and Z minus is stronger. And that means Y will be kicked out. So Y minus is going to be a weaker base and Z minus is a stronger base. So a stronger base comes in and kicks out the weaker base. But if Z was a weaker base and Y minus is a stronger base, then the opposite will happen. Then the Z will be kicked out and you will go back to your starting material. And if both Z and minus have, Y minus have very similar basicity, then you will get a mixture of starting material and product. You will get both reactant and the product left over. So this is what the gist of the reaction of carboxylic acids is. If Y minus is very weak, it's gonna leave and you're gonna get the addition of the nucleophile and the Y minus is eliminated, okay? And if Y minus is stronger, then Z is gonna be kicked out and you're gonna get back your starting material. Now, how does it reflect on the different carboxylic acid derivatives we had? We have acid chloride, we have acid anhydride, we have esters, we have carboxylic acids, and we have amides. And we know that this is the activated form of carboxylic acid, that these are the reactive compounds, and amide is the least reactive of the lot. So the question you might ask is that why acid chloride is the most reactive? The reason why it is most reactive is the chloride that is present on the COCl. Cl minus is a very, very weak base. It's a weakest base of all. So if it's a weak base, it can be eliminated quite easily. So that means this is the most reactive species, followed by an acetate or a carboxylate ion. And carboxylate ion is also easy to remove. So is alkoxide, OH minus, and NH2 minus and OH minus. These are strong bases. So these are strong bases over here. And the strong bases are not going to eliminate easily. That means from the RCONH2, if you want to remove minus NH2, it's going to be very hard because this is a very strong base. So you can't just remove that easily. While the Cl minus here can be removed very easily because this is a very, very weak base. Another way of finding out which is a strong base or a strong acid is usually by writing their conjugate species. If we are saying that these are bases, there is Cl minus, all these are bases. And if you write the corresponding acids of these bases, Cl minus, the acid is HCl. Acetate, the acid is carboxylic acid. Alkoxide, the acid is alcohol. For OH minus, the conjugate acid is water. For NH2, the conjugate acid is ammonia. And we know HCl is strong base. Acetic acid is less stronger. less stronger. So you can either check the basicity of your leaving group by looking at the pK value of the corresponding conjugate acid, or you can check the basicity of your anion as it is given there. So there are two ways to check which group is going to be able to leave quickly. One is it a weak base? If yes, then that is going to be eliminated very quickly. If it's a strong base, it's not going to be eliminated quickly, so it's going to be least reactive. But you can also look at the corresponding conjugate acid, and the strong acid will have a weak base, and hence is going to be eliminated. So you can either look at by looking at the basicity or the corresponding acidity of the conjugate acid. Now let's look at the reactions of the carboxylic acid derivatives, like we did in the case of aldehydes and ketones, starting with the Grignard reagent. You may recall that we looked at the reactions of the Grignard reagents with aldehydes and ketones, which is represented on this lower reaction here. We learned that the R group here in Grignard reagents act like a nucleophile. It attacks the carbonyl, forming this intermediate magnesium salt. And when you add aqueous acid, it forms the corresponding alcohol. We learned that before. What if we react an ester with the Grignard reagent? What will happen? In the same way, as we learned before, this R minus will come and attack this carbonyl to give you this intermediate species. Remember, in aldehydes and ketones, we have a group here which cannot be lost. But in the case of carboxylic acid derivatives, this group shown in red can be removed in that reaction. So if that happens, if that is gone, you're going to get a corresponding ketone formed from the ester. So what has happened here is ester, we started with an ester, and the ester is now converted to the corresponding ketone because this is a ketone. And we also know that ketones can react with Grignard reagents as well. That's shown in the next slide. So this ketone here can react with the second equivalent of the Grignard reagent to give you a corresponding alcohol compound. So that means in case of carboxylic acid and their derivatives, the reaction with Grignard reagent happens twice, not once, but twice. In the first step, you form a ketone from an ester. And in the second step, the ketone is converted into the corresponding alcohol compound. So it reacts to form the corresponding alcohol compound. And in that alcohol, the two R groups are exactly the same. So the two R groups are the same in case of the ester functionality reacting with the Grignard reagent to give you an alcohol. And this alcohol is a tertiary alcohol. Okay, and exactly the same thing happens. Oh, sorry, this is another example here, which is a real example. We got ethyl magnesium chloride reacting with the ester to form a ketone. And this ketone reacts again with the Grignard reagent to give us the tertiary alcohol. And you can see that two groups are the same. So this group and this group here are the same in this case. They are coming from your Grignard reagent. And the product you get is a tertiary alcohol in this case. And that's the product you get. Okay. All right. What about hydride? If you have a hydride, what will happen? So we learned about the Grignard reagent where the nucleophile was R minus. What happens if the nucleophile is a H minus compound? In the H minus, the same thing happens. You got hydride here, H minus. And again, just to remind you that an aldehyde, for example, reacts with the H minus to give us the corresponding alcohol. H minus attacks here. This goes up. And then when you work up with water, you get the corresponding alcohol. And 2 hydrogens are there, which comes from your starting reagent. So when we do this reaction with ester, hydride reagent attacks the ester first, like it attacks the carbonyl. And then the minus charge comes around and kicks OCH3 minus out because this is a leaving group. And this is the strong base, strong nucleophile compared to OCH3 minus. And you get the aldehyde. And the aldehyde reacts with another hydride to give us the corresponding alcohol where the carbon has now 2 hydrogens. When the carbon has 2 hydrogens and an OH group, these kinds of compounds are called as primary alcohol. So the end product of this reaction is a primary alcohol. So that means a carboxylic ester derivative or carboxylic acid derivative, which is an ester, will react 2 times with hydride to give you an alcohol compound. Okay. While in the case of aldehydes and ketones, you only need 1 hydride to give you the corresponding alcohol. There you have 2 successive reactions with the hydride ion to give you the corresponding primary alcohol. Okay, that's enough about the reaction with the Grignard reagent and the reaction with a hydride reagent. The reaction we're going to talk about now is the reaction between a carboxylic acid and an alcohol. This is a very, very old, very famous reaction. It is called as Fissure Esterification. This reaction is known for 100 years. And basically, this reaction involves taking a carboxylic acid and reacting with an alcohol. And the end product of this reaction is formation of an ester, and water is eliminated in this reaction. I was telling you earlier, the carboxylic acids are very sluggish to react. So it takes a long time for this reaction to take place. If you take carboxylic acid, you heat it with alcohol, you can heat it for days and days and days, and you will get the formation of the ester, but it takes a long time. It's a very sluggish reaction. This reaction, I was telling you, historically, it is very important. This is the first way in which esters were made. So a long time ago, the only way the esters were made was reacting an acid with an alcohol. And it's still used today. But it's not a very efficient reaction because you can see from these arrows here that this is an equilibrium reaction. However, if we can somehow shift the equilibrium to the right-hand side, this reaction can be useful if you can push it to the right-hand side. And there are 2 ways you can push this reaction to the right-hand side because it is in equilibrium, so you can push one side to the other side. One way to do that is if you add excess of one of these reagents, you can put the reaction on the other side. Typical equilibrium reaction, if we use excess of this reagent here, it will push the equilibrium to the side, right-hand side. And typically in these reactions, the alcohol is always used in excess. You can add excess amount of alcohol. For example, if you're trying to make a methyl ester, you put excess methanol. Ethyl ester, you put excess ethanol. Or another way to push this reaction forward is if we can remove this water from the reaction. If the water is formed and you remove this water, you can force this reaction to go forward. So that means you can play around with the conditions to push your reaction to the right-hand side. So the question you might ask is that what is the mechanism of this esterification reaction? How a carboxylic acid is converted to the corresponding ester? The mechanism of this reaction is that the carboxylic acid here, since this reaction is catalyzed by an acid, it protonates this carbonyl group. The H goes there, that OH becomes oxygen, becomes positive. And the alcohol oxygen comes and attack that carbonyl, pushing that pair of electrons onto the oxygen to give us this tetrahedral intermediate. And there's a positive charge on this oxygen. You get a proton transfer, you get removal of that proton, and that proton is taken over by this oxygen over here to become OH2 plus. And then this pair of electrons come around and kick the water out. So there's a water eliminated in this reaction. You get loss of water, you get loss of this OH minus as water, and your nucleophile R-O has added onto the carbonyl over there. And then you basically release that proton, which is attached to that oxygen, and that proton is recovered in the reaction. Because this is a catalyst, acid is acting as a catalyst, and catalysts are not consumed in the reaction. That's why the H plus comes out as it is in this reaction, and you get the formation of the ester in this reaction. This is the mechanism how an alcohol reacts with carboxylic acid. In some ways, it's very similar to the aldehydes and ketones, but the only difference is that this group here can be lost in the reaction to give you the corresponding ester compound. This reaction is a very useful reaction. Just give you two examples. The carboxylic acid here, the benzoic acid we talked about earlier, if you react with excess amount of methanol, which is an alcohol, and you add catalytic amount of sulfuric acid, which is an acid, and you will form this compound here, ester plus water. And this reaction is used industrially as well. The polyester material, which we use for shirts and a lot of different kinds of products, is made by reacting an acid with an alcohol. In this case, the acid is a dicarboxylic acid, and the alcohol is a diol, also double alcohol, called ethylene glycol. If you heat these things together, you will form a polymeric material, and that polymeric material is called as polyester. And that's the basis of the formation of this polyester material. It's just taking a simple Fissure esterification reaction, reacting carboxylic acid with alcohol to form a polymer with lots of ester bonds or ester groups present in it. Okay, so this is an application of the Fissure esterification reaction. But like I was telling you, this reaction is very sluggish. The carboxylic acid reacts with the alcohol very slowly, and you have to manipulate the equilibrium to put the reaction forward. On the other hand, if you take an acid chloride, the activated form of carboxylic acid, and react it with alcohol, you will get the formation of the ester instantaneously. You will get this reaction to work within minutes, and it'll be like reaction will be over by the time you mix those two things together. So this is a much better way or easier way of preparing the esters rather than reacting carboxylic acid to form the ester. And this is a very convenient reaction, and it can use a base as a catalyst to remove HCl that is formed as well. Similarly, instead of acid chloride, if you use an acid anhydride reacted with an alcohol, you will again form the ester very easily, and you will get one of the product from here eliminated as a carboxylic acid in that reaction, and that give you the corresponding ester product. So what I have shown you is that the carboxylic acid, yes, can react with alcohols to form esters, but the reaction of the activated forms of carboxylic acid with alcohol is much more faster than just reacting acid with the alcohol. So what we have looked at is how to form the ester. Can we also check if the reverse reaction can be carried out? That means, can we take an ester and hydrolyze it back to the carboxylic acid and the alcohol? So what we're going to do now is look at the exact reverse reaction. And you might ask me, why do we want to hydrolyze the ester back to the acid? Because we just made it from the acid. The reason is hydrolysis of the ester is a very important reaction from industry point of view. And I'm going to show you a reaction in a minute, which is used to make soap in industry. And the soap is made by hydrolyzing an ester. So what is hydrolysis of ester? Hydrolysis of ester is that the esters can be converted back into the acids and alcohols from which they were formed by reaction with aqueous acid or aqueous or alcoholic hydroxide solution. So that basically is trying to tell us that we can use either H3O plus acid. H3O plus also means acid. We can take aqueous acid, or we can take hydroxide, which can be sodium hydroxide, or it can be potassium hydroxide, to convert the esters into the corresponding carboxylic acid. And this can be an aqueous sodium hydroxide or alcoholic sodium hydroxide. That means you can dissolve that in alcohol or water. So in this reaction, this is exactly opposite of what we learned just now. You start with the ester instead. You use excess water, and you have acid as a catalyst. And this reaction here gives you the corresponding acid plus the alcohol. Your starting materials back when you do this hydrolysis reaction. Let's see what's the mechanism. I'm not going to spend a lot of time on this mechanism. It is exactly same as the one we saw in the formation of the ester. The only difference is the attacking species here is water. And if you may recall earlier, the attacking species was OH alcohol when we formed the ester. Now we are doing the opposite reaction. So the attacking species is a water molecule rather than an alcohol. But the steps are exactly the same. You protonate the oxygen, you attack with water, you get a proton transfer from here to over here. Then you get an elimination of the alcohol then you have your acid present as protonated, and then you just recover your acid and the alcohol from this reaction. So exactly opposite. An acid is not consumed in the reaction. H plus is recovered after the reaction. We used it in the beginning and we get it back afterwards. So exactly the opposite of forming the ester. But this hydrolysis here can also be carried out by using a base like sodium or potassium hydroxide. And this is reaction when it's catalyzed, I shouldn't say catalyzed, it's a reaction which is promoted by the sodium and potassium hydroxide, because the hydroxide is going to be consumed in this reaction. It's not going to be catalyst, we're not going to recover it at the end. It's going to be utilized in the reaction. And this type of reaction is often called as a sponification reaction. A sponification reaction is the one which is used to make soap. The soap which we use at home, all are made by this sponification reaction. So what happens in the sponification reaction is that we take an ester and we react it with hydroxide, and it forms a salt of an acid. Instead of getting COH, we get CO minus, and if this is sodium hydroxide, you'll get a sodium salt plus the alcohol compound. And this salt of the acid is actually the soap which we use in household. But the question is, what is the R group here in soap? And we'll come to that in a second. First of all, the mechanism, how sponification happens, how the base is able to react with the ester in this case. The OH minus here attacks the carbonyl, just like all nucleophile attacks the carbonyl. This comes around and kicks this out, and that becomes R-O minus. We call that an alkoxide, and the carboxylic acid. Alkoxide is a base. This is an acid. So acid will give away that proton to the base to form a salt, and you get the alcohol molecule and a salt. Now let's see how soap is made. So we learned what the chemistry behind the soap formation is. How can we utilize this to actually form soap? And this is an example of a reaction on how soap is made. And soap comes from fats and oils. You can make a soap from any fat or oil. You can take sunflower oil, you can take canola oil, you can take palm oil, you can take any oil you have, and you can treat that with sodium hydroxide. What you would get is a glycerol molecule, and you will get sodium salt of what we call fatty acids. Because fats and oils are made up of two things. One is what we call the central glycerol molecule. This molecule here in the middle is called as a glycerol molecule. It's like a triol, it's like an alcohol, which has 3 hydroxyl groups present in it. And these hydroxyl groups are present as esters in the fats and oils. The fatty acids are attached onto these alcohols via this ester link. So all fats and oil, it doesn't matter where the fat comes from, it doesn't matter where the oil comes from, they have the same general structure. There's a glycerol molecule in the middle. There are fatty acids attached to it via the ester link. So if you react it with a base like sodium hydroxide, you will get sodium, salt, or fatty acids. And this is what is called as soap. So the price of this soap depends upon how expensive is your oil. You can buy, for example, almond oil, soap made from almond oil. And that is going to be more expensive because the fats and oils come from the almonds. You can have a cheap oil, you will get a cheap soap. But the process to make this soap is exactly the same as shown here. Reacting with hydroxide to get the sodium salt to form the corresponding salts of the fatty acids, which are your oils. And similarly, any other ester can be hydrolyzed to form the carboxylic acid this way as well, by using water or acid, aqueous acid, or base to form the acid. All right, let's have a little break now for a few minutes. And you can think of questions in the meantime. So let's have a few minutes break. I'm gonna get a drink of water and I'm gonna let you think about some questions. And when I come back, you can ask me the questions on the subject we have covered so far, and then we'll continue after that. So let's have a break for a few minutes while you think about some questions.
Sure. Baik semuanya, kalau misalkan ada pertanyaan bisa disampaikan di kolom chat atau bisa ditanyakan langsung ke Prof. Naresh. Khususnya yang materi ini ya, senyawa asam karboksilat. Tetapi boleh gitu ya bertanya untuk materi-materi yang lain juga. Oke. Kira-kira ada yang bingung dengan reaksi senyawa karboksilat?
Okay, I'm back. Are there any questions so far on the fats and oils and making soaps?
Yeah, please students, if you have any questions, about not only soap, or maybe you can ask about carboxylic acid or other reactions if you want. Yeah.
Any carbonyl question?
Yeah, because I know that some of the students are learning the monofunctional compounds, and then some of them learn about the polyfunctional compounds. So
Okay.
yeah, I see here.
Or maybe we can have questions at the end if you like. If
Sure.
yeah.
Yeah, sure. Actually, I have also a question.
Okay.
Yeah. So you can continue then with the,
Continue. Okay.
yeah.
All right. Let's try to finish the carboxylic acids esters today if we can, and then we can start with alkenes. Okay. Let's continue. The next reaction we're going to look at is very similar to the reaction with alcohols. What we're going to do the reactions with amines instead. And you will see in a minute that the reaction of carboxylic acids with amines is also a very important reaction biologically as well as industrially. And the carboxylic acids, they will react with the amines to form what we call amides. So the OH group will be gone and will be replaced by the amine group, and we call that molecules amides. But one thing to remember is that if you react a carboxylic acid with an amine, we know that amines are basic in nature. RNH2 amine is basic. Carboxylic acid is an acid. So if you react an amine with an acid or react an acid with a base, what do you get? You get a salt, right? So if you take carboxylic acid, you got this amine, which is a base. Base can accept a proton, and carboxylic acid can give away a proton. So if that happens, the first thing that is going to happen is you're going to form a salt, which is going to be like the ammonium salt of the carboxylic acid. But if you take this salt and heat it up at very high temperatures, like greater than 200 degrees Celsius, this salt here will get converted to the corresponding amide. And this is not a nice way to make amides, because at 200 degrees Celsius, many organic compounds, they break down. So although this is a process by which you can make amides, but it is not a very good process because it requires a lot of heat. And the reason for this slowness of the reaction is that the carboxylic acids are not very reactive to start with. They can form a salt with an amine, and that's what makes their reaction really sluggish, and you need very high temperature. But this is how nylon is made. I don't know. Many of us use nylons. We use nylon in our socks. We use nylon in slacks, and we use nylon in ropes. Many different applications of nylon. But that's how nylon is made. Nylon is basically an polyamide compound. It is formed by mixing a diamine together with a carboxylic acid to form a salt. And then the salt is heated at very high temperature, like 250 degrees Celsius, leading to the formation of the amide bonds. And this is what we call nylon. Nylon is a polymer, and the reaction is shown here. So this is how nylon is produced on a very large scale. You take carboxylic acids, which is a diacid, you take diamine, you mix them together at room temperature. The acid forms a salt with the amine. And when you heat that salt at high temperature, you get a polymer. You get the formation of this compound or this functional group here called amide. So a carboxylic acid will react with an amine at high temperature to give you an amide. An amide bond is very important in biology as well as chemistry. But an easy way, a much easier way of making the amide is that you use the activated form of carboxylic acid, and we know that the activated form is an acid chloride. We can react it with an amine. For example, ammonia, we get amide. If you react it with a primary amine, this one with a little zero at the top is called as a primary amine, and the two with a little zero is called as a secondary amine. If you react it with a primary amine, you can get a secondary amide. Secondary amine give you a tertiary amide, and the primary amide is here, primary amide. So primary is when the nitrogen or the oxygen got two hydrogen attached to it, then is called as a primary alcohol or primary amine. This is a primary amide. And this is a secondary amide because there's one hydrogen, no hydrogen on the nitrogen is a tertiary amide. So this is a very convenient, easy way of making the amide molecules by simply reacting the activated form of carboxylic acid with an amine. The mechanism is very simple again. The amine is a nucleophile, attacks the carbonyl, and this is a very good leaving group, as I told you before. This comes around and Cl minus comes out happily, and the H plus, which is extra here, combines with Cl to form an HCl, and you get the amide molecules. The acid chloride, the activated form of carboxylic acid, is so active that it can also react with water as well. You can imagine oxygen is your nucleophile. It will attack the carbonyl, and then you lose your Cl minus again here as HCl to give you the carboxylic acid back in this case. So activated forms are very reactive. They can react, but also you have to be careful that the water doesn't react with the activated form, because if water reacts with the activated form, you're going to get acid, and acid is slow to react. So these reactions are typically carried out with the precaution that there is no water present in your reaction. And the same way you can use an acid anhydride. We also learned that the acid anhydride is the activated form of carboxylic acid. It can also react with amine to give you the corresponding amide compound. And even esters can also react with amines to give you the amides as well, because amides are the least reactive or most stable compounds. You can convert acids, esters, activated forms of carboxylic acids to the corresponding amide compounds by reacting with ammonia. One thing which is very important, and you should know, that there is a fundamental difference between an amide. So never confuse amide with an amine. An amine is a compound where the nitrogen is directly attached to a carbon. So this is an amine compound. And amines are basic compounds. They are like bases. While amides, they are neutral compounds. So amides are often confused with amines, but they have very different properties. Most importantly, amines are basic substances where amides are neutral. The amines are basic because they can accept a proton. That's why they're basic. The amides are not basic. So remember that. Never confuse an amide with an amine. And the reason why amides are not basic is that it has a resonance structure where you can put the negative charge on oxygen and positive charge on nitrogen, like this double bond N. That makes this molecule not basic at all, because if you are a base, if amine is a base, amine can form RNH3 plus. When it accepts a proton from an acid, it becomes NH3 plus compound. Your amide already has this plus here, so it cannot accept a proton. So that means it's not a basic compound, it's neutral compound. So remember that amines and amides are two different species. Just like the esters, the amides can also be hydrolyzed in the presence of acid or base. That means amide will hydrolyze to give you the acid plus the amine back. Just like the ester gave us the corresponding acid plus the alcohol. So it can be acid catalyzed, or it can also be base catalyzed. And acid catalyzed is a catalytic reaction where acid is a catalyst, while the base catalyzed is where base is actually used up in the reaction. So just very similar to ester. There's no much difference at all. All I have done here is change that oxygen to the NH group to start with an amide. You may recall that earlier mechanism we saw was for the hydrolysis of the ester, and the ester had this structure. You had an oxygen, then you have an oxygen, and then you had an R dash. This was our ester when we looked at the hydrolysis of the ester. Hydrolysis of the amide is exactly the same mechanism, no difference. Protonation, attack of the nucleophilic water, oxygen attacking the carbonyl, transfer of this proton onto the nitrogen, then elimination of this amine as a salt, or sorry, as a free amine, and the carboxylic acid as protonated species, and acid is recovered after the reaction. Acid is a catalyst, is not used in the reaction, but the mechanism is exactly the same. Okay, and the amine can form a salt with the acid, obviously, to give us the ammonium compound here. Similarly, this hydrolysis can also be carried out in the presence of a base like sodium hydroxide or potassium hydroxide. But we can't use this process to make soap because soap comes from the ester. But the reaction is a bit like a sponification reaction where OH minus attacks that carbonyl. Amine is removed. You get a carboxylic acid and a nitrogen minus. This is going to take away that hydrogen away from that acid to give you the free amine and the carboxylate. And if you add some acid at the end of the reaction, then you can get this ammonium salt formed for this compound. Otherwise, it'll be just present as the carboxylate species with the sodium or potassium salt with whatever you used here. I think we're nearly coming to the end of the carboxylic acid derivatives. This is, I again don't want you to spend too much time on this. It's just another transformation of the amide compound to the corresponding cyano compound by removal of water from this particular compound by using a strong hydrating agent. And this type of compound is called as a nitrile. And this is obviously a cyano group. And it's just showing that amide can be dehydrated to give you the corresponding nitrile compound. One advantage of this reaction, for example, is that if you want to put a cyanide into your molecule, typically you use potassium cyanide or sodium cyanide. You take an alkyl halide, you react it with the cyanide to get the cyano compound. However, cyanide is very toxic. Sodium cyanide or potassium cyanide is very, very toxic. In our lab, we have to actually store this chemical in a safe because it's so poisonous. but it can be used to make, used to convert alkyl halide into cyano compound. But another way of making the cyano compound is taking an amide and dehydrating to get the cyanide. So there is no potassium cyanide or sodium cyanide required in this reaction. So this is a useful alternative or safer alternative to make the cyanide compound. And this is the absolutely last slide. We talked about esters and amides, and you can also have cyclic esters and cyclic amides. So for example, here, this is a cyclic ester. This is a cyclic amide. And these cyclic esters and cyclic amides are very important compounds. And the cyclic esters are called as lactone compounds, and the cyclic amides are called as lactam compounds. And they're very important biologically as well. And this is an example of what we call a beta lactam. And beta lactam structure is present in antibiotic, amoxicillin antibiotic or ampicillin antibiotic we use, which is used quite a lot for killing bacteria. So whenever there's a bacterial infection, the antibiotic is based on this structure here. I think I'll stop here for now. And that finishes the section on the carboxylic acid derivatives. And I'm quite happy to answer questions now related to carboxylic acids. And then we can move on towards the alkenes as the next topic. There is no questions in the chat. So if anybody has any questions, feel free to ask or feel free to put in the chat and we'll try to answer those.
Yeah, thank you, Prof. Naresh. So for students, if you have any questions, here there are Valencia. Valencia mungkin punya pertanyaan. Atau siapa ini? Ai Susanti ada? Okay, seems like everyone is too shy to ask. Yeah, because I know it feels like a lot of reactions going on.
Yes, I know.
Yeah, sometimes, yeah, I know that the students have a hard time to maybe not memorize, even not memorize, but yeah. So actually, I have question, Prof. Naresh. It's here we have in the chat from Kabiru.
Oh, right.
Yeah.
Okay. Any method for conversion of primary amides to primary amine? Okay, that's a reasonable question. So what we are asking is, can we convert a primary amide into a primary amine? Let's see if I just find some space. Okay, maybe I can talk here. This is a primary amide. RCONH2 is a primary amide. And the question is, can we convert that into the corresponding primary amine? And the primary amine will be a structure which will have a CH2 NH2. This will be an example of a primary amine because the nitrogen has 2 hydrogens. So this is a primary amine. This nitrogen has 2 hydrogen. This is also a primary amide. So this is a primary amide and this is a primary amine. So the question is, how do we convert primary amide into a primary amine? Maybe we can ask the audience if anybody knows the answer. What are we doing? We are doing 2 things here. We are trying to reduce this C double bond O into CH2. When we add hydrogen into a molecule, we call that reduction. We are trying to reduce it. And that means we need a reducing agent. And we learned about 2 reducing agents in the reaction we have covered so far. And those reducing agents we learned were the hydride reagents, which were H- reagents, because we are adding hydrogen. So it could come from H- in this case. We learned about 2 sources of hydride. One was lithium aluminium hydride, and the other one was sodium borohydride. And we learned that sodium borohydride was a weaker reagent and lithium aluminium hydride was a very strong reagent. So if you want to convert a primary amide to an amine, then you need the strong reducing agent lithium aluminium hydride. So if you take your amide and react it with lithium aluminium hydride in the presence of a solvent, which will be like an ether solvent or THF, tetrahydrofuran, because you can't use methanol or ethanol in this reaction because lithium aluminium hydride is a highly reactive reagent. And I can tell you that because I have used it in the lab myself, and it's a gray colored powder. And if you throw some in water, you will get sparks coming out because you see the fire coming out straight away, because when it reacts with water, it produces hydrogen, which catches fire. So a primary amide can be reacted with a strong reducing agent to give you the primary amine. So the answer to your question is yes, we can convert the primary amide to the primary amine by reduction. That's good. There was one answer already in the chat. That's good. Any other question?
Oh, Kabir also asked.
Okay, Huffman degradation. We didn't cover Huffman degradation. I think it's a first year a monofunctional reaction. So we'll save the Huffman degradation for higher years. I think it's beyond the scope of the first year monofunctional reactions. So let's save that for next time.
Yeah. Thank you, Kabir, for your question, and Rabia for answering the reduction. Any questions? Actually, Prof. Naresh, what I want to ask is about the acid anhydride. So if the R group is both the R groups are unsymmetrical, like which one is the leaving group when we react acid anhydride with the nucleophile?
Okay, so the question is, what if we have a CH3? That's a tricky question. If you have a mixed anhydride, OC, say if we take an acidic formic anhydride like this, and we react it with an amine. So the question is, do we get the formation of RNH, COCH3, or do we get the formation of the corresponding compound, which will be RNH, C double bond O H? Do we get the formation of a formamide, or do we get the formation of that compound. So in this case, the leaving group will be H, C double bond O, O minus formic acid or formate. While in this case, the leaving group will be CH3, C double bond O minus, right? So there's not going to be a lot of difference, as you can see, between the basicity of the formic acid or the acetate ion. So I'm going to give you some homework, Vidya. I'm going to ask you to check the conjugate acid of this compound is formic acid, right?
Yes. Yeah.
HCOH. And the other side is going to be acetic acid. So if you check the pKa value of acetic acid and formic acid, you can tell from that which group is going to be a better leaving group. Oh, there's going to be only slight difference between the two. And from that, you can get the answer which is going to predominate, or you're going to get a mixture of the two compounds. If the pK is very similar, then you might get a mixture. But if there's a difference in pK, you can get one forming over the other. So that's homework for you.
Sure. Thank you.
Okay.
Okay. Yeah. Because what I found in most the textbooks, the R group that they are presented in the textbooks, most of them are symmetrical, so it doesn't matter which one.
That's true. But sometimes when you're doing a formulation reaction, you normally use, or sometimes you can use a mixed anhydride, acidic formic anhydride, and you can get a formyl substituted amine. Yeah, but check that.
Sure.
Okay.
All right. Thank you, Professor Naresh. Is there any question from students? I hope the explanation is clear for you.
Oh, there is something in the chat. Attendance.
Yeah, attendance. Yeah.
All right. Maybe I can. I got couple of minutes, I can start the alkenes or wait till the next lecture.
Sure.
Let's just quit this for the time being. Stop sharing. Just trying to close my screen. Stop sharing. Okay, so I just stop sharing for the time being. And I try to bring in the other slides. I won't go into too much detail, but at least I will introduce the topic which we're going to be talking about in the next lecture. So we're going to be in the next lecture talking about alkenes. And the alkenes are very interesting compounds. And we're going to be covering the structures of alkenes. We're going to talk about nomenclature of alkenes and more reactions. We're going to be looking at reactivity of alkenes as well. So the difference between a carbonyl compound and alkene is alkenes have a C. Oops, sorry, I just going ahead of myself. The alkenes are C double bond C compound. The two carbons are linked together by a double bond, and these can be substituted. And the similarity, I suppose, to the carbonyl compounds is that the carbonyl compounds have an oxygen attached to it, while here you have two carbons attached. And both carbons here are sp2 carbons, and there is obviously a pi bond and a sigma bond present between the two carbons. And that pi cloud here is the electron density that is present in a carbon-carbon double bond. Let's look at start with the nomenclature, that how do we give names to alkenes? How do we give scientific names to the alkenes? We know that the common name for, say, for example, if you have a molecule which is a CH2, double bond CH2 is ethylene, we call that an ethylene compound. What if the carbon chain is longer? How are you going to name that compound? And I got some examples here for you to show you how you might name these compounds. So I've drawn that thing at a wrong place. I just erase this for the time being so that it doesn't crowd the structure over there, and go back to get my pen. Okay, so how do we name alkene compounds to start with? So there are a few examples here, and there are certain rules we have to follow when we name the alkene compounds. The first is you look at the longest continuous chain containing the double bond. So there are 1, 2, 3, 4 structures here. If you look at this structure, it has a 4-carbon chain. This has a 4-carbon chain. So that means the name is going to be based on butane. Butane is the 4-carbon chain. And whenever you have a double bond present in a molecule, carbon-carbon double bond, it's going to have that ene present at the end. If it's a 4-carbon, then it becomes butene. If it's 6 carbons, then it becomes hexene. And if there's 8 carbons, it becomes octene, and so on. So that's the first rule. You look at the longest continuous chain that is present in your molecule. Name is going to be based on that. You can see here that the longest chain that is present with the double bond is 6 in this molecule. Although if you don't take into account the double bond and you go 1, 2, 3, 4, 5, 6, 7, 8, there's an 8-carbon long chain present. But what we are looking for is the longest chain where the double bond is present in the molecule as well. So we are not looking for the longest carbon chain only. We're looking for longest carbon chain containing the double bond. It must contain that functional group, and that is only 6 carbon long. So that's the first rule. Longest continuous chain containing the double bond. And then the second rule is that you have to give that double bond the minimum numbering possible. So it means you start your numbering in such a way that the double bond gets the minimum numbering. So if you start from this end, here is 1, 2, 3, 4. If you start from this end, then it'll be 1, 2, 3, 4. But you can see here, if you start from that end, the double bond carbon is at position 4. But we want to give that carbon a minimum number where the double bond is present. So means the correct numbering will be 1, 2, 3, and 4 rather than the other way around. And in this case, we just put 1 in front and call it a butene. So that means the double bond is starting at first position in that molecule. Similarly, if the double bond is present here in the middle, so in this case, it doesn't matter whether you go 1, 2, 3, 4 this way or 1, 2, 3 this way, the double bond is always present or starts at the 2 position. So hence the name 2-butene. In the case of 6 carbon, if we start from this end and call it like this, 3, 4, 5, and 6. This way, the bond starts at the 4 position. It'll be 4-hexene, but that's not correct, because if you start from the other end, the double bond comes at the 2 position and we call it 2-hexene. So you need to make sure that the double bond carbon where it starts get the minimum numbering. And the same thing applies here. The 6 carbon is the longest carbon chain with the double bond in it. And then you start from that carbon over there. And then at the 2 position, you have this group that is present. And this is a 3 carbon group. 3 carbon group comes from propane. 3 carbon compound is alkanes are called propane. And the corresponding group is called as a propyl group. The double bond is starting at 1 position, so that's hexene. The propyl group is present 2 positions, so you call that 2 propyl 1 hexene. So that's the way you number and name the alkene molecules. I think we're nearly out of time, so I will stop here for today, and then we will continue with the alkene nomenclature as well as the stereochemistry that is present in alkenes, cis and trans isomers, and then the reactions of alkenes in the next lecture. But I'm still happy to answer questions if you have any. And then we will continue with this alkenes in much more detail at the next lecture.
Yeah, so thank you, Professor Naresh. We have 3 lectures left, right?
Yeah.
3, so the next lecture will be next week.
Yeah.
At 6, and
the
then
2 lectures next week. Yeah.
Yeah, 6, 7, and then 13. The last one will be on 13. So yeah, we will still be having 3 lectures with Professor Naresh. So for today, before we end this lecture, do you still have any question? Is there any?
You can ask question from any section we have covered so far.
Yeah.
Vidya.
Yeah. Oh,
Can
Bu
I
Amel.
ask? Okay. Prof. Naresh, nice to meet you again. All right. I want to ask about the Fissure Esterification or the common esterification reaction. For Fissure Esterification is use acid catalyzed. But is it possible for the esterification reaction using a base catalyzed?
Okay. That's an interesting question, because typically the Fissure esterification can be carried out with acid as a catalyst, but also you can do Fissure esterification by not using an acid catalyst, but removing the water from the reaction. And there's a special apparatus which is used for this purpose. It's called Dean-Stark apparatus. You may have heard about that. It's like a glass tubing which collects water. Yeah. So if you do the reaction, for example, in a non-polar solvent like toluene, and you boil your acid with alcohol without any acid present, and start collecting all the water from your condenser as it is formed, the reaction can be driven forward. But trying to use base as a catalyst, it is a bit hard to imagine unless you use a base which is, see, the problem with using a base will be that you will remove the proton from the carboxylic acid with that base. So let me just share the screen and try to draw something to explain this concept. So I'll just bring up the screen. So let's just look at this screen here. So if I have a carboxylic acid and I want to react that with a base, or with an alcohol in the presence of a base. So that's the acid. And say if we got alcohol represented by ROH like this, if we use a base, what's going to happen is the base is going to remove this proton quite easily. And if this proton is removed, you're going to get a CO minus forming, right?
Right.
And this species is going to be resonance stabilized.
Yeah.
And it can form oxygen minus on this side and C double bond O on this side. Okay, so this oxygen here is going to reduce the reactivity on that carbon, because typically alcohol, say for example, if you have an acid, it will attack the carbonyl. Say if we had the acid, sorry, I'm not need to draw it again. If the alcohol will attack the carboxylic acid like this, but if there is a carboxylate present, because of that negative charge, because you need a slight positive on that carbon and a slight negative on that oxygen for it to react. But if this positive charge here is neutralized or stabilized or reduced by this O minus, carboxylate is not going to be able to react with a carbonyl compound very well. So that's the reason why we don't use base as a catalyst in the reaction of carboxylic acids, because the base will form a salt or a carboxylate, and carboxylate wouldn't react with the alcohol as readily as a carboxylic acid. So that's why you can do the reaction in the acid catalyst or without the acid catalyst.
Okay, Prof. Thank you. It's very clear. So when we want to use the esterification, so we just use acid catalyst or without acid, but we can use a basic.
No, we can't use base. Yeah.
Okay. Thank you, Prof, for the clear answer.
Okay.
I clearly understand about the concept now. Thank you.
All right, thank you, Ibu Amel, for the question. So, is there any question from? Sometimes it's a bit difficult to know if to know the students, because I can't see students' face. Yeah, that's the perk of having online learning.
Yeah, and then sometimes it's a bit slow to write a question on the chat. I
Sure.
find myself.
Sure.
Although the young students are very fast, they can type very quickly.
Yeah. Does it happen there at when you did learning online learning at UNSW?
Yeah, that's right. We have online learning, and some students are very quick to type. Before you can think, they can write a question. And now when we have staff meetings also, we have questions on the chat. And some young academics, they're very fast.
Yeah. Yeah, because yeah, we every day I think we use the social media when you type
Right.
and then scroll everything. All right, from students, because right, is there anything you want to ask to Professor Naresh? So I would like to remind you, we still have 3 lectures left. 2 lectures will be in the next week on Monday and Tuesday. And then the last one will be on 13th of December. So I think just before the exam, the final exam.
Yeah. And we will finish alkenes and alkynes in the next 3 lectures. So.
Sure. So yeah, so please be ready for the next lectures. It will be about alkene and alkynes.
Maybe if the
Yeah.
students can read little bit before coming to the lecture, then they can ask better questions or more questions.
Yeah. Do you have any recommended reference or textbook?
There was a textbook mentioned on my lectures in the alkenes section. Do I still open? Yeah, I can actually share. Is Pearson? Is book by Pearson Education? I can email it to you if you like, Vidya, and then you can let them know.
Yeah, sure.
I think it's Paula Jacobs. I think book. I will try to find it for you.
Sure. Thank you. We sometimes use the Fessenden.
Yeah, that's fine as well. Any book is fine.
Yeah.
You can just look through the reaction of alkenes and alkynes, and we will be covering a lot of those. Any organic chemistry book will have it.
Yeah, and especially for the alkenes, there are a lot of reactions. Yeah, can occur on the alkenes.
Yeah.
So yeah, please be ready because maybe some of the because the final exam also will cover the alkane alkynes. Yeah, especially for the students in our department. All right, is there any question or you want to say something, or maybe Prof. Naresh would like to say something before we end this lecture?
No, I think we're pretty good. It's almost 8:30 p.m. at nighttime here. So yeah,
it's time to recharge your body actually.
Yeah, I know, that's right. It's a long day.
Yeah, I know. All right, so maybe if students don't have any question, maybe we can end this lecture. Prof. Naresh, thank you very much for your lecture, for your explanation, and I hope all the students here can understand, or at least can have better understanding on especially the carboxylic acid. And we will continue with alkene and alkynes. So see you again next week. Thank you very much, Prof. Naresh. Have a good rest. Have a good night. Thank you, Ibu
Prof.
Gaby, Ibu Amelinda, and all students. See you again next week. See you.
Bye.
Bye.
See you.
Terima kasih, Vidya.
Thank you, Prof.
Ya, terima kasih untuk mahasiswa semuanya, begitu ya. Sampai bertemu lagi minggu depan. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi
Atur nuhun, Ibu.
Nah, sami-sami nuhun Bu Amel.
Ya, Ibu, lama tak berjumpa.
Ketemunya di sini aja.
Ya, sehat-sehat, Bu Gaby.
Ya,